Imagine for a second that you are standing a few feet away from this massive cylinder of solid steel.
Right.
And it's locked into a machine spinning at an incredibly high speed, like maybe 3,000 or 4,000 revolutions per minute.
Which is terrifying on its own.
Yeah, exactly. Now imagine taking a heavy, hardened cutting tool and just shoving it directly into the side of that spinning metal.
Oh, man.
Think about the extreme, violent physics at play right there. The pressure pushing back against that tool, it isn't measured in a few pounds, right? It's measured in thousands of pounds of force.
Easily.
And if the setup holding that spinning mass of steel slips, even by like a fraction of an inch, that heavy piece of metal instantly becomes a kinetic projectile. It flies out, shatters the reinforced polycarbonate windows of the machine, and just destroys tens of thousands of dollars of sensitive equipment before you can even blink.
It is a brutally hostile environment. I mean, we look at these sleek, modern manufacturing machines on a factory floor, with their clean enclosures and touchscreen interfaces, and they seem so controlled.
Yeah, very sterile.
Right, but inside that cutting zone, you are dealing with absolute controlled chaos. You're essentially tearing metal apart at a microscopic level. And the physical forces generated, they're constantly trying to just rip the machine itself apart.
And navigating that chaos is really the focus of today's deep dive. We are exploring a stack of technical notes and engineering documentation on this obscure but absolutely vital piece of industrial engineering.
Yeah, the anti-retreat function.
Exactly, the anti-retreat function of the tailstock on a CNC lathe. So our mission today is to demystify this highly technical mechanism. We want to understand the extreme physics at play here and, explore how some surprisingly simple mechanical concepts prevent these incredibly advanced million-dollar machines from literally tearing themselves to pieces.
It's fascinating stuff.
Okay, let's unpack this. We've established the terrifying stakes of metal machining. But to understand how the machine fights back, we really have to look at the invisible enemy causing the danger in the first place, right? The documentation refers to this force as axial thrust.
Yeah, axial thrust. Because when that cutting tool engages with the spinning metal, the force of that impact and the resistance of the material, it doesn't just disappear.
Right. Physics dictates the energy has to go somewhere.
Exactly. The tool is pushing massively hard against the side or the face of the part. And that force translates into a vector that travels straight down the length of the metal along what machinists call the Z-axis, directly into the tailstock center.
Okay.
So that rearward push of immense power, that is your axial thrust. It's this continuous, violent pressure trying to shove the tailstock backward, away from the cutting zone.
And historically, like the way you might try to fight that backward push on an older or maybe less rigid machine is by relying on simple friction.
Sure, just clamp it down.
Right. You crank down on some heavy bolts, clamp the tailstock tightly to the cast iron machine bed, and just kind of hope the friction holds.
Sure.
But the documentation makes it really clear that under the extreme load of aggressive, modern CNC machining, normal friction clamps are a spectacular failure.
Oh, absolutely. They just slide right backward.
It makes me think of, well, it's like trying to hold a door shut against a battering ram just by leaning your body weight against it.
That's a great analogy.
You're relying entirely on, like, the friction of your rubber shoes on a slick floor. At a certain point, no matter how hard you push against that door, the incoming force is going to overpower the coefficient of friction, and you're just going to slide backward across the room.
And friction is incredibly conditional, right? It relies on massive surface area, immense clamping pressure, and critically, the absolute absence of lubrication.
Which is ironic for a CNC machine.
Totally ironic, because the inside of a CNC machine is essentially a bathtub. It is constantly flooded with high-pressure liquid coolant, and the ways of the machine are continuously pumped full of slick, lubricating oil to help the components slide smoothly.
So you're trying to create an immovable friction lock in an environment specifically designed to be as slippery as possible.
Exactly. You simply cannot trust friction when 3,000 pounds of axial thrust are trying to push that tailstock away.
Which is exactly why the anti-retreat mechanism was developed in the first place. The sources detail that this mechanism, it just throws friction out the window entirely and relies on what they call a positive mechanical interlock.
Right.
Instead of just pressing down hard and hoping for the best, the machine bed actually features a heavily toothed rack or a series of deep slotted channels cast and machined right into the iron foundation of the lathe.
And then the machine drops a heavy, hardened steel locking block directly down into that rack.
Yeah, so to go back to the door analogy, it's like you stopped leaning your body weight against the door, and instead you've dropped a thick steel deadbolt straight down into a reinforced hole in the concrete floor.
You've fundamentally changed the physics of the situation.
Exactly. You aren't relying on two surfaces gripping each other anymore. You've created a solid mechanical barrier. The tailstock physically cannot move backward unless the axial thrust is powerful enough to shear a solid block of hardened steel cleanly in half.
And shearing that block, I mean, that would require forces far beyond what the spindle motor could ever generate. It is an absolute physical hard stop. Right. But the documentation does highlight a few different engineering approaches to this same problem. Like, the rack and pinion deadbolt is the most common, but there are other brilliant solutions like self-locking worm gears used in the positioning mechanism.
Yeah, I noticed that in the notes, and the worm gear concept really stood out to me, but I wanted to make sure I understood the physics of it.
Yeah.
Because a standard gear set can be spun from either direction, right? Like if you spin the motor, it turns the wheels, but if you push the car, the wheels turn the motor.
Right, it's back-drivable.
But a self-locking worm gear completely breaks that two-way street.
It does. It's this elegant manipulation of geometry. In a self-locking worm drive, you have a threaded worm, which looks basically like a heavy screw, meshing with a toothed gear or a rack. Because of the incredibly shallow, specific angle of the threads on that worm drive, the motor can effortlessly turn the screw and drive the tailstock forward or backward. But if an outside force, like our axial thrust, tries to push backward against the system, that linear force cannot rotate the screw.
Because the angle is just too shallow.
Exactly. The backward thrust simply binds against the side of the thread profile, turning the linear pressure into internal static friction against the housing. It physically cannot be back-driven. The harder you push against it, the harder it locks itself into place.
That is so cool. But I also noticed the documentation brings up high rigidity guideways as an alternative to the deadbolt or the worm gear. The notes describe them as being ground perfectly flat and pre-tensioned to remove any loose gaps.
Right, the guideways.
But if you're just grinding the metal rails flat and clamping down on them really hard, aren't you fundamentally just returning to the friction method? Like, how does that actually solve the slipping issue compared to dropping a physical deadbolt?
It does sound like a step backward, but high rigidity guideways operate on a completely different scale of force. We aren't talking about a simple clamp here.
Okay.
In these specific setups, the tailstock is pulled down onto tapered, wedge-shaped rails using massive hydraulic cylinders, and they're generating tens of thousands of pounds of downward pull. Because the rails are wedged, pulling down also forces the metals together laterally.
Oh, so it's squeezing from the sides too.
Yeah, and the surfaces are ground so perfectly flat that when that hydraulic pressure is applied, the microscopic peaks and valleys of the two metal surfaces actually interlock. It borders on temporary cold welding.
Wait, really? Cold welding?
Basically, yes. It creates a rigid bond that functions identically to a solid mechanical barrier, but it requires incredibly sophisticated manufacturing of the machine itself to achieve those perfectly mated surfaces.
Wow. So reading through these different solutions, I had a thought about the technology running all of this. We were talking about highly advanced modern CNC lathes.
The best of the best.
Right. And these machines have sensitive computers monitoring the cutting force in real time. They look at the spindle load, they track the servo motor strain, they have closed-loop feedback systems operating in milliseconds.
Very true.
So if the computer can just sense the pressure rising and instantly tell a servo motor or a hydraulic valve to push back harder, why do we still rely on dropping heavy steel blocks into toothed racks or binding up worm gears? It seems almost, I don't know, archaic to use a chunk of heavy metal when you have gigabytes of processing power at your disposal.
It's a great question, and the distinction really comes down to the difference between an active system and a passive system.
Active versus passive.
Right. No matter how sophisticated the software is, or how fast the processor can send a signal to a servo motor to push back, you are relying on a continuous, unbroken chain of active energy. Active systems are vulnerable.
I see where you're going with this.
Yeah, imagine a tiny piece of grit making its way into a proportional hydraulic valve, or a momentary voltage dip in the factory's power grid, or just a tiny sensor glitch that lasts for 50 milliseconds.
Just a tiny blip.
Exactly. If any of those links in the chain fail for even a fraction of a second, the active pressure drops, the tailstock instantly slides backward under the cutting pressure, and your entire setup is just destroyed.
So a heavy steel deadbolt dropped into a rack is the ultimate passive system. It requires zero electricity, zero processing power, and zero hydraulic pressure to maintain its strength once it's engaged.
Exactly. You can pull the plug on the entire factory, and that tailstock is still locked exactly where you left it.
That makes perfect sense.
Software optimizes the process, but mechanics secure it. True engineering elegance relies on recognizing where digital intelligence ends and the unbreakable laws of mechanical physics begin. You cannot hack a solid steel block.
No, you definitely can't.
You cannot cause a worm gear to glitch. They provide guaranteed fail-safe resistance.
Okay, so we built this completely immovable, infinitely rigid wall.
Yes, we have.
But as I was diving deeper into the sources, I realized that creating this absolutely rigid wall introduces a completely new, massive problem.
Oh, yes, it does.
The engineers solved the axial thrust issue, but in doing so, they created what I'm calling the thermal paradox.
It is the inescapable reality of friction and heat. I mean, the metal cutting process is not really cutting like slicing a tomato with a knife.
Right.
You are using a tungsten carbide tool to physically wedge and shear away material through plastic deformation. This process requires massive amounts of energy, and the vast majority of that energy is instantly converted into profound thermal energy.
So it gets hot, like really hot.
Very. The temperature at the cutting edge can easily exceed 1,000 degrees Fahrenheit. The steel chips flying off the part often turn deep blue or purple entirely due to the extreme heat.
And the part itself is acting as a heat sink, absorbing a significant portion of that thermal energy. We're not talking about the metal getting a little warm to the touch. We are talking about extreme structural heat.
Yep.
And in the physical world, when metal gets that hot, it undergoes thermal growth. The piece of steel you are cutting actually expands in all directions.
Right, thermal expansion.
A solid steel shaft that is 3 feet long might grow by several thousandths of an inch during the machining process, which sounds tiny to a layperson, but in an environment where tolerances are measured in 10,000ths of an inch, that is a massive, violent shift in dimensions.
It really is. And if you take a heavy steel shaft and lock it firmly between two completely immovable objects like the massive spindle chuck on the front and our perfectly rigid, dead-bolted tailstock center on the rear, and then you pump hundreds of degrees of heat into that shaft.
The expanding metal has nowhere to go. It's completely trapped.
Exactly. And trapped thermal expansion is a destructive force. If the shaft is thin enough, the pressure will force the metal to bow outward in the middle, turning your perfectly straight shaft into a warped, unusable piece of scrap.
Yikes.
But if the shaft is thick and rigid, it won't bow. Instead, it will push outward against the spindle and the tailstock with near infinite force.
And the documentation notes that this trapped thermal expansion will push directly into the main spindle housing, right? Compressing the precision angular contact bearings until the steel balls literally crush permanent dents into their own steel races.
Yes, it destroys the spindle from the inside out.
Which brings us to the solution. To safely handle this thermal expansion without compromising the rigidity of the setup, operators use a spring-loaded live center for these hot parts instead of a solid single-piece dead center.
That's right.
And here is where the paradox really jumps out. I have to play devil's advocate here based on the notes.
Let's hear it.
We just spent all this effort, all this brilliant engineering brain power, designing heavy steel blocks, automated hydraulic clamps, and self-locking worm gears to completely stop any backward movement whatsoever. We built an impenetrable wall.
We did.
And now the documentation says the solution to the heat is to just stick a bouncy spring on the front of that impenetrable wall. Doesn't adding a spring completely defeat the entire purpose of the rigid anti-retreat function we just built?
I know. It looks like a massive contradiction on paper. You're building a fortress and then putting a screen door on the front.
Exactly.
But this is where we have to separate the mechanism into two distinct, isolated systems. You have the tailstock body and the tailstock center.
Okay, break that down for me.
The tailstock body is the massive cast iron housing weighing hundreds of pounds that sits on the machine rails. The center is the specific cone-shaped piece of hardened metal that slides into the front of that body and physically touches the spinning workpiece.
Ah, okay. So the anti-retreat mechanism, the deadbolt, is locking down the massive cast iron body.
Correct. If the massive body slips backward under the macro-level forces of the cutting tool, even a fraction of a millimeter, the entire setup loses structural integrity. The part deflects away from the tool.
Right, that's bad.
But the spring-loaded live center operates on a micro level.
Yeah.
And we aren't talking about a coil spring from a mattress here.
Right, it's not a slinky.
Far from it. These life centers use stacks of Belleville washers. They are heavy, conical disc springs made of thick steel. They require thousands of pounds of pressure just to compress a single millimeter.
So they are incredibly stiff. They basically act as a heavy-duty shock absorber, calibrated specifically to the immense pressure of thermal expansion.
Exactly. The Belleville washers yield just enough to safely absorb the microscopic thermal growth of the hot metal part as it lengthens. They maintain a constant high-pressure grip on the part, accommodating the heat expansion, while the main tailstock body remains securely bolted and dead-bolted to the machine bed by the anti-retreat mechanism.
Wow.
You are isolating the microscopic, inevitable shifting of thermal dynamics from macro-level, violent forces of the cutting tool.
It's a brilliant balancing act. You're holding a volatile, growing, violently spinning piece of metal, and you have to be totally unconditionally rigid against the tool, but just flexible enough internally not to snap the part or crush your own bearings.
It's incredible engineering.
Which leads us to the dark side of this equation. Let's look at what happens when that balance fails. Like if a hydraulic seal blows and that deadbolt doesn't drop, or an operator forgets to lock the manual lever.
It gets ugly fast.
The documentation details exactly how catastrophic a tailstock slip really is, and it all comes down to the geometry of the machine.
Yeah, to understand the destruction, picture a long steel cylinder. The front end is clamped firmly into the jaws of the spinning chuck. The rear end has a small hole drilled into it, and the cone-shaped tailstock center is pressed firmly into that hole, supporting it.
Okay, got the picture.
For the machine to work properly, the center point of the chuck and the center point of the tailstock must share the exact same, mathematically perfect, invisible center line.
And when you are pushing a heavy cutting tool into the middle of that shaft, the axial thrust travels back into the tailstock.
Right.
So if the anti-retreat mechanism fails and the tailstock slides backward by just a millimeter, that cone-shaped center slips right out of the hole in the back of the part.
Yep. That perfect alignment is instantly gone, and the part completely loses its rear support.
And remember, this piece of metal is spinning at 3,000 revolutions per minute, while a cutting tool is shoving hard against the side of it.
The moment it loses that rear support, the tool pushes the metal off-center.
Yeah.
Now you have a heavy off-center mass spinning at high speed. The centrifugal force takes over, creating an immediate feedback loop.
Oh, man.
The part bends outward away from the tool and begins whipping wildly in a massive blur.
It's like holding a heavy spinning jump rope, perfectly taut with a friend. You've got one handle, they've got the other, and you're spinning it as fast as you can.
Yeah, exactly.
If your friend suddenly lets go of their handle, that rope doesn't just fall limply to the ground. The kinetic energy causes it to violently whip out of control, wrapping around your arm or smashing into anything nearby.
A perfect way to visualize it. And in the lathe, that heavy whipping vibration travels straight down the metal shaft and directly into the main spindle headstock.
Which is where those expensive bearings are.
Exactly. The spindle houses incredibly precise, highly engineered bearings that allow the chuck to spin perfectly smoothly. That violent off-center radial whipping introduces massive shock loads that those bearings were never designed to handle. It overloads and destroys them almost instantly.
But the spindle isn't the only casualty. The documentation specifically highlights the damage to the turret.
Right, the turret.
The turret is the heavy rotating carriage inside the machine that indexes and holds all the different cutting tools. When you are machining a complex part, you aren't just cutting the outside. You frequently use the turret to drive long drills or reamers straight down the center line of the rear of the part to hollow it out.
And if you are driving a 1-inch thick solid carbide drill bit straight into the back of a spinning steel shaft, the axial thrust trying to push the part backward into the chuck is massive.
So if the tailstock is supporting the part and it suddenly slips backward under that drilling pressure,
the geometry of the cut instantly shifts. The spinning shaft deflects, and that thick, brittle carbide drill bit binds up inside the hole.
and carbide doesn't bend.
No, it shatters, and it doesn't just break the tool. The spindle has so much kinetic energy that it keeps spinning for a fraction of a second, grabbing the broken shank of the drill and jamming it violently sideways.
Oh, that sounds awful.
That massive impact force travels straight back into the turret housing.
And the turret relies on a complex internal mechanism, usually a highly precise set of interlocking metal teeth called a curvic coupling, to lock itself into position.
Right.
So that sudden, violent shockwave from the snapping drill just shears those interlocking teeth clean off. You've just ruined a $20,000 indexing mechanism in the blink of an eye.
That is the literal sound of a machine crash. 1 millimeter of slip cascades into shattered drill bits, a destroyed turret coupling, ruined precision spindle bearings, massive repair bills from the machine manufacturer, and a production line that is halted for weeks.
Just from 1 millimeter.
Just one. The anti-retreat mechanism isn't just about ensuring the cut leaves a smooth finish on the metal. It is the literal safeguard between a highly productive factory floor and a catastrophic, violent failure.
Knowing how disastrous a slip can be, relying on a tired human operator on a 12-hour shift to manually pull a lever and perfectly drop that deadbolt every single time seems incredibly risky.
People get distracted, mistakes happen.
And that brings us to the evolution of the machine controls and how this anti-retreat function is handled in modern programming. Think about the shift from a machinist wrestling a heavy wrench on an old manual lathe to a modern operator standing at a console.
It's night and day. On those traditional manual machines, the operator physically shoves the heavy tailstock body along the cast iron bed to get it into position. Then, they use a large wrench to manually turn a cam lever, which engages that heavy anti-retreat block into the bed rack.
It is purely physical labor.
Yeah, but on a programmable CNC lathe, the entire process is automated. The operator just uses the computer interface, and the machine uses hydraulic cylinders to pull the tailstock along the rails and fire the locking block into place.
The documentation explains that this automation is handled using specific lines of code called M codes. When you look at CNC programming, you primarily hear about G codes, right? G codes handle the elegant, complex geometry of the cut, like telling the tool to move in an arc or cut a precise taper.
Exactly, but you don't use G codes for the tailstock.
Right, because the tailstock isn't doing the intricate cutting, it's providing brute force auxiliary support.
So the control system relies on M codes, which are essentially the machine's state commands.
Like on or off switches.
Basically, the operator types M10 into the program. The computer reads that tiny keystroke, sends an electrical signal to a solenoid, a valve opens, and a massive hydraulic cylinder fires down, forcing the steel block into the rack. And M11 reverses the flow and unclamps it.
But here is where the engineering philosophy really shines through the documentation. It explicitly states a crucial caveat. Whether you are running a fully automated million-dollar multi-axis CNC machine or an old-school manual lathe from the 1970s, the anti-retreat function itself remains a fundamentally mechanical feature.
Yes.
The M codes don't add complex algorithmic safety checks. You aren't writing code to dynamically calculate the thrust and offset it with varying servo pressure. The elegant software is simply being used to execute the low-tech action of dropping a metal block into a slot.
It perfectly illustrates how modern manufacturing blends domains. You use software to optimize the efficiency, like positioning a tailstock rapidly via an M code without breaking the operator's back, but you rely on the unbreakable analog laws of mechanical physics for the ultimate safety net.
It's the best of both worlds.
And there are specific machining scenarios where this physical safety net isn't just a backup, it's an absolute necessity to cut the material at all.
Yeah, the sources single out hardened steel, specifically materials with a hardness rating of HRC 50 or above, as the ultimate test for these systems.
Because hardened steel has been heat-treated to change its crystalline structure, it is incredibly tough, highly abrasive, and it aggressively resists the cutting tool.
Okay.
When the carbide insert hits hardened steel, the metal doesn't want to shear away smoothly. The tool acts more like a blunt plow, forcing its way through. That extreme resistance causes the axial thrust forces to skyrocket compared to cutting softer materials like aluminum or mild steel.
So if you are trying to machine a long, slender shaft out of hardened steel and you haven't dropped that anti-retreat deadbolt, that massive thrust will instantly push the tailstock back.
Right away.
But the documentation clarifies a really interesting point about the geometry of the part itself. It's not just the hardness of the material that demands the anti-retreat function, it's the shape of the setup.
Exactly. If you take a short, thick slug of that exact same hardened steel and you clamp it entirely inside the deep jaws of the main chuck, you don't use the tailstock at all.
Because there's nowhere for it to go.
Right. The thrust vector is pushing the part directly into the solid steel face of the chuck. The machine absorbs the force effortlessly. The terrifying axial thrust only becomes a problem when you are machining a long part that hangs far out of the chuck, because that thrust vector is now actively trying to push your rear support structure away down the rails.
So we've covered incredible ground today. We started by defining the terrifying forces of axial thrust, thousands of pounds of continuous pressure trying to rip a machine setup apart.
We did.
We explored how engineers fight back not with friction or software, but with positive mechanical interlocks, like dropping heavy physical deadbolts into cast iron racks, or binding up shallow worm gears to create an immovable wall.
And we navigated the thermal paradox, understanding how stacked Belleville washers create a spring-loaded live center stiff enough to hold the part, but yielding enough to safely absorb the massive pressure of microscopic heat expansion,
Yep.
all while the tailstock body remains rigidly locked down.
And we looked at the terrifying reality of a machine crash, how a single millimeter of slip unleashes kinetic energy that destroys precision spindle bearings and shears turret indexing couplings in a fraction of a second.
It's sobering stuff.
It really is. And finally, we saw how the elegance of modern M codes interfaces perfectly with brute force mechanical blocks, proving that even the most advanced programmable systems fundamentally rely on immovable physical reality, especially when pushing cutting tools into abrasive hardened steel.
You know, for you listening, this deep dive into the obscure, highly specific mechanics of a CNC lathe tailstock is actually a perfect metaphor for the automated world we live in.
How so?
We are entirely surrounded by advanced software, predictive artificial intelligence, and seamless digital automation. But no matter how advanced the code becomes or how fast the processors run, foundational stability always relies on solid, unseen, physical mechanisms doing the heavy lifting in the background. Software is merely a layer of control. It is only as reliable and only as safe as the mechanical reality it operates within.
That is a profound way to look at the invisible engineering around us. And it leaves me with one final thought based on everything we unpacked from the documentation today.
Let's hear it.
We know that in the most advanced, expensive machines on the market, highly sensitive computers are constantly monitoring the servo loads and cutting forces in real time, ready to adjust pressure and optimize the cut.
Right.
But we also know this is an environment filled with extreme violent vibration, devastating shock loads, and high heat. So what happens when the delicate digital centers feeding that vital data back to the computer inevitably begin to degrade?
It's bound to happen eventually.
Exactly. Over time, in that hostile environment, a sensor will drift or a connection will loosen. Could we reach a point where a multi-million-dollar machine eventually hallucinates its own stability?
That's a scary thought.
Right. Could machine literally tear itself apart, crushing its own bearings and shattering its own tools because the software implicitly trusts a faulty, degraded sensor reading over the absolute analog certainty of a mechanical deadbolt? It's something to chew on the next time you put your full, unquestioning trust in a completely automated system. Think about the invisible deadbolts holding your world together.